Hi, everyone. So we start the class. So turn on video. And I have commented on all of your final project plan as long as you have already submitted. You can check the comments. So in the first year, when I taught the 50-30, I didn't ask students to submit a final project plan, but some projects have trouble. So I think the best way to improve the quality of presentation is to get feedback beforehand. So that's the reason for presentation, the project plan. So yeah, you can read it and start the analysis. And today, at first, I discuss the presentation guideline. And after that, we continue to chapter 13, logistic regression. And chapter 12, probably we won't have much time, but if we have some time, that we will cover a few of the sections on Thursday. Okay, so first I will share the screen and do it. Okay. Yeah. Okay. Share a screen. I uploaded this final project plan, the final presentation guideline here. So yeah, first, the presentation is approximately 12 minutes. I would say 8 to 30 minutes. If 7 minutes, that's fine, but this is suggested time. So after 12 minutes, I said it's already 12 minutes. So wrap up a presentation in 1 minute. So after 30 minutes, I will just force to quit the presentation. So you cannot present all materials. So my suggestion is the time your presentation twice before your actual presentation to make sure that your presentation can be finished on time. And the format of presentation, usually the statistical presentation, applied statistics presentation have this format. So first we have the introduction. So this is brief explanation of background and your objectives. Then the data description. So explain the data source, meaning of variables and sample size, maybe sample unit as well, and other essential information. So especially if you have not included especially to make sure that you include the data source of your data set. And the methodologies that described what models are used. You use the linear regression, then what's the response, what's the predictor variables, and explain theory behind the models if the models are not discussed in the course. I think only a few of you have methods that are not covered in the lecture, but if you have any, they briefly explain the model. And then probably this is the largest portion, the empirical results. So demonstrate and interpret empirical results and its implications. S is missing here. Yeah, so especially, for example, if you do regression, at first interpret the estimate. So suppose the coefficient of x is 2, then what that means? Maybe x is age and y is, I don't know, blood pressure. Then as x increases by 1, the 1 year older, then blood pressure is increased by maybe the 2 millimeter Hg or something. So you interpret that. And especially the sign of the coefficient is important, whether age positively affects the blood pressure or negatively affects the blood pressure. And also the p-value, maybe t-value, those things are important. And the described statistics and figures Yeah, and so this is statistics class. So some of the students focus on the statistical estimation, but it's really important to have some descriptive statistics and the graphs to show what really data tells. Yeah, and again, so this is statistics class. So the model diagnostics, like the residual plot, QQ plot, and the test results and the interpretation of the results are often more important than the final prediction models, such as the model chosen by the stepwise AIC or cross-validation. Yeah, so signs are important. And also I usually use the word response and predictor in regression model, but the regression model, they just explain the relationship between y and x, not causation between y and x. So explain what indicates your result indicates. So x explains y, but that situation depends on your data, right? So if the y happens after x, maybe x is the data from 2000 and y is data from 2021, that is actually prediction. But in many of other cases, just it explain the relationship between x and y, but not really the causality. So just to clarify what's the implication of your result. And conclusion, they usually short conclusion, and maybe possibly discuss possible future work, research topics related to your project. And slides, my suggestion is 12 to 20 slides for a 12 minutes presentation, but it really depends on how much information each slide contains. And make slides understandable to the audience. So usually you only have 1 minute or less for one slide. So everything should be clear. So if it's a very crowded slide, then probably your classmates cannot really see what it means. And avoid R code and raw R output in your slides. So make it in a beautiful graph or tables and omit the R code. So to see slides within a few seconds or maybe 30 seconds or so, I think the simple slides are really necessary. So objective of final presentation is to show analytical results to the audience and not to demonstrate R code. So in my lecture slides, the one objective is to explain R code. So it includes many R code, but your objective isn't really that explanation. So the focus on your results and implications. Yeah, so if you have some statistical models that describe the method by equations, that's easier to see, especially if you put it in a mathematical formula, the equation format, it's really easier to see. So if you see R code, the audience see the R code, it takes some time to see what's really happening. And the submission, I ask you to submit presentation slides and R code. And if your presentation is in video, a link to the presentation video. And R code will not be graded except for special cases, such as some important information is missing in slides. And for video presentations, I think most of you can present in class in Zoom. But you can see here that some of you have to make video presentations because I cannot really accommodate all presentations in class. So the Dalber, Nicholas, the Maitri, and the Evan, Kirsten, Claudia. So that you have to make video presentation. So just see the format in detail. So basically, I will ask you to provide the link to your YouTube channel or Google Drive. You don't really have to make it public, but you have to provide link so that everyone who clicked the link can see your video. Grading criteria of the presentation, the clarity of introduction, meaningfulness of objectives, and quality of data, and appropriateness and clarity of statistical methods used, and the demonstration and interpretation of results, and the votes by students. So these 5. And the submission deadline for Zoom presentations, I ask you to submit slides and R code before presentation. So presentation start at 6:30. So you have to submit the slides and R code by 4 p.m. The R code isn't really essential, but especially slides, the 4 p.m. Usually I don't see R code. So video presentations, submit all materials, slides and R code and the video link by 11:59 on your presentation date. So that's it. Do you have any questions on presentation guideline? Okay, so this file is available online, so in Canvas. So you can check it in detail if you would like. Okay, I will check the attendance now. Okay. Then we go to chapter 13. I think that some of you have to use logistic regression in your project. So I would like to finish most of the part today. Yeah, and actually before that, I have one announcement. I sent you an email earlier today. Oh, sorry, my mic isn't very clear. So I sent you an email about the Math 5740 theory of interest. So currently enrollment is 7, and we have to have, I think, maybe 8 to 12 students. I don't really know the exact threshold, but to run the course that we need a little more enrollment. So I would say if you have more than 5% chance to register for the course, just register for it for now. And if you decide to drop later, that's fine. But if you have more than 5% chance, then register the course by December 3rd, so that we have lower risk that course is canceled. So the theory of interest is about the mathematical application of, the mathematical side of the fixed income products, such as bond or loan or annuities. And actually it is directly related to the actuarial exam, the financial mathematics. So if you're interested in both, mathematics or quantitative area and finance, then I think it's fun course. And it's too difficult. It's not too difficult course. So it requires only the Math 2020. So I would say that it's slightly more difficult than 2000 level course, but if you have already finished one of the 5000 level stat or math course, that is very good. Anyone taking, I got one comment. So anyone taking actuarial exam FM, I'd recommend it. Yeah, actually, yes, certainly if you think about actuary as a future career, certainly you have to take it. Yeah, thank you. On campus, yes. That is the face-to-face traditional course. So just the blackboard and chalk course. So just traditional mathematics course. It's on campus. Okay, so do you have any other questions on that? No. Okay, so I will share the screen to discuss chapter 13. Okay, so the logistic regression. So just a quick review. So logistic regression have continuous predictor, also maybe possibly other predictors such as the categorical predictor. But the point is the response is binary, so 0, 1. So for example, whether patient is malignant or benign, or sorry, I think that I have some trouble about. Okay. So
yeah, so the response is categorical. For example, in marketing data, 1 is successful and 0 is unsuccessful or something like that. And mathematically speaking, always we say 1 as success, even if this means the patient is malignant, just in statistical term. So 1 is called success. Yeah, so our idea is just to use the linear model to deal with this binary response. But we have 2 problems. So one is the y is bounded. So y is between 0 and 1, right? And the second thing is the y is discrete. Y is either 0 or 1. It can only take 2 values. So we have to modify the linear model to accommodate this situation. And to make the response as continuous, the idea is to take expectation or to take probability. So we consider probability of y is equal to 1. So, our realization is either y is equal to 1 or 0, but we consider given predictor values, what's the probability of y is equal to 1? Suppose x is the height of a person, y is whether the person is 18 years old or more. Based on x, 145 centimeter. So what's the probability that y is equal to 1? Maybe 40% or something like that, maybe even lower than that. So we consider probability. Then probability is a continuous variable. So it's much closer to the real valued response. So we consider the probability. And the probability is expectation, right? So the y is either 1 or 0. So expectation of y is probability of y is equal to 1. Right? So because expectation of y is probability of y is equal to 1 times 1 plus probability of y is equal to 0 times 0. So this is probability of y is equal to 1. So expectation. So we have already taken expectation, so we don't have error term. So that is another difference. Okay, so now everything becomes continuous, but the problem is pi is still bounded by 0, 1. So that is a problem because if we consider any possible the predictor values, right-hand side may be 1.5 or right-hand side maybe negative 0.8 or something like that. Then that is actually not good because the response is between 0 and 1. So predicted value should be between 0 and 1. 1.5 does not make any sense. Always worse than 1, right? Because the response is either 0 or 1. So the idea is to use the link function. So link function is the function of this shape. So the domain is 0, 1, 0 to 1. But the range is from negative infinity to positive infinity. So such function. Then we consider f of pi is equal to linear combination of x1 to xp. So in this way, the left-hand side is also the real valued variable whose range is entire real numbers. So then this model is consistent with the property of f of pi. Okay, so now the left-hand side is just the totally continuous variable. So we can do regression. So this is generally called the generalized linear model. If we have f and we have expectation here, then it's called the generalized linear model. So the logistic regression we study in this chapter is a special case of generalized linear regression. So generalized linear model, generalized linear regression. So that is covered in STAT 6840 that will be offered in fall 2024. So that you can register for it if you are interested in. So this course will be offered every 2 years. So if you are interested in, just take it. And what's the exact function f? So as long as f is from open interval 0, 1 to entire real numbers, then it satisfies the necessary condition, but the often we use this function specifically. So that is the log of pi over 1 minus pi. Maybe you can plug in numbers. So pi is probability. So you can plug in 0.9, then pi is equal to 0.9. Then the logit function of 0.9 is the log is natural logarithm. So 0.9 over 1 minus 0.9. So this is the log of the 9. So it's a kind of large number, maybe 2 or 3, maybe 2.5, maybe. And how about logit of 0.1? So 0.1, then this is the 0.1 over 1 minus 0.1. So this is log of 1 over 9. So that is small. That is about negative 2.5. So you can see this ranges from 0 to, the negative infinity to positive infinity. So as pi gets smaller, logit of pi approaches to negative infinity. As pi approaches to 1, the logit of pi approaches to positive infinity. So that is the property of this function. Oh, sorry. What happened? Yeah. So that's it. Okay. Yeah. And another common function used is the phi inverse of pi, where phi is the CDF of standard normal distribution. So that means the phi is integral negative infinity to, the phi of x. The phi of x is integral of negative infinity to x, and the f of x dx, maybe f of t dt. And the f of x is standard normal distribution, so bell-shaped curve. So x, y, and y is equal to f of x here. So the phi of x is the area under this curve, like this. So this is phi of x. And this is the point x. Yeah, so this is a kind of the most common, the CDF, the cumulative distribution function. So in statistics, if we consider the function from R to 0, 1, probably the normal CDF is the most common function. So that is another natural idea to define f. And the most of the time that we use this first function, the logit function in this slide, and the logit function, this regression model is called logistic regression model or logit model. And the second one, therefore, normal CDF, actually the inverse of normal CDF. So this is called the probit model. That is also commonly used. And the one good thing about the logit function is that the inverse of the function also has the specific formula. So the f of pi is defined as the log of pi over 1 minus pi. But if you just do some algebra, then you can see that the f inverse of pi is exponential of pi over 1 plus exponential of pi. So you can see that, for example, if pi is equal to 0.5, then f inverse of pi is what? That we can calculate this as the expectation, exponential of 0.5 over the 1 plus exponential of 0.5. So this yeah. So this is f inverse of pi. So it should be between 0 and 1. So if we put 0.5, sorry, the pi is between 0 and 1. So this ranges from negative infinity to positive sorry. F inverse pi of this. So this is equal to, this is between 0 and 1. Sorry, this is between 0 and 1. So for any number, pi, maybe pi is a little bit probably misleading because this is not probability, but the fitted value. So maybe I should say that maybe it's logically the same, but we should put some different letter for any letter. Maybe just we get maybe what is good. This is, yeah, anything is fine. Maybe just we put t or something. So t. So we put the fitted value t, then we can transform this t to probability. So if t is equal to, for example, maybe the 3 or something, then f inverse of this is exponential of t over 1 plus exponential of t. So this is the exponential of 3 over the 1 plus exponential of 3. So this is pretty large number. So e to the third power is about maybe the 20. So this is probably around 0.95. So using the fitted value, so t is equal to 3. So that can be obtained by this side. So if x1 to xp are given, we can calculate this value. And suppose this is 3, then we can input 3 into this f inverse, the inverse logit function, then we can get the probability 0.95. So today's one quiz that asks to transform this fitted value into a probability. So again, so this model, the left-hand side is continuous scale, but if we want to transform it into a probability, then you have to use this inverse f. So inverse logit function for the case of logistic regression. Okay. And do you have any questions so far? So in terms of model, this is it. So this is logistic regression model. So next we discuss the estimation of logistic regression model. So remember that the linear regression model. So linear regression model, maybe the simplest case is y is equal to beta naught plus beta 1x plus epsilon. And how to estimate beta naught and beta 1? Basically, we minimize summation of epsilon square. So if we have n observations, then we minimize the sum of square of epsilon i's. So epsilon 1 square to epsilon n square. Then this is equal to actually the yi minus beta naught minus beta 1xi square. And remember that this was a quadratic function of beta naught and beta 1. So quadratic function is probably the the easiest function to minimize, right? So that's why we do some linear algebra that we calculate beta naught and beta 1. But in logistic regression, that estimation is a little complicated. So basically, we use the maximum likelihood estimator. So we want to maximize the likelihood by optimizing the parameter beta naught and beta 1. So suppose that y is the response variable, x is the matrix for predictors. And we use just the same notation as the multiple linear regression. and xi be the ith row of x. So this may be a vector. So this is xi1 to xip. Then likelihood function is defined by this. So likelihood function of this ith observation is basically f inverse of xib beta if yi is equal to 1. So f inverse of xib beta is equal to pi I, right? So this is basically the fitted value of the logistic regression, and we use the inverse logit function to make it probability. So if yi is 1, so basically that observation is successful, then success probability is the fitted value. So maybe suppose that the success probability is 0.8, and actually the ith observation is successful, then 0.8 is the likelihood. And if that observation is not successful, it's a failure, then 1 minus pi I is the likelihood. So if pi I is 0.8, the 0.2 is the likelihood, because our success probability, estimated success probability is 80%, but actually it fails. So our likelihood is 20%. So the other way around. So based on these probabilities, that we can calculate the likelihood function. So basically that we take the product of this likelihood for all observations. So to be specific, basically that we have to separate the case, we have to separate the successful cases and the failure cases. And successful cases that we have to multiply the all pi i's. And for failure case that we multiply all 1 minus pi i's. So that is the likelihood. So yeah, and that is if we take logarithm, then we can represent that this way. So yeah, so this is the function to optimize. We want to maximize this with respect to beta. With respect to beta. So that is our estimation method. Okay, so if we have multiple observations, for example, I is equal to 1, 2, 3, in reality, we have hundreds of observations, but suppose we only have 3 observations, and the pi I is 0.3 and 0.6 and 0.8, and our actual observations are, for example, 0 and 1, then the likelihood is 0.7, right? So we failed. So 1 minus pi I is 0.7. And again, it's failed. So this is 1 minus 0.6, so 0.4. And if the third observation, it's successful. So the L is pi I. So these 3 probabilities are used for calculating likelihood. So basically this times this times this is likelihood. So that's the the concept to optimize beta. So we have to maximize this with respect to beta, but this is very complicated function because the F inverse is e to the power x over 1 plus e to the power x. Then in place of x, we have to put this linear combination of betas. And further, we calculate the log of that. So it's very complicated function of beta. So unlike the linear regression model, the optimal beta cannot be estimated analytically. So we don't have simple formula such as x transpose x inverse the x transpose y. We cannot really use this. So basically we need the numerical method to maximize the likelihood function. And statistical packages often use the iteratively the reweighted least squares. So basically, we can exploit the method of least square some way, but we have to do the iterative calculation similar to Newton-Raphson method. Yeah, so if we use the optimization function in R, such as optim function, we can calculate the beta. Yeah, actually. Yeah, but the good thing is that this logistic regression, even though this function is very complex, this is known as the concave function. Concave function is like this. Okay, so this is not concave, sorry. They're like this. So actually the local, we only have the one local maximum. So we don't really have any problem with reaching the local maximum problem. I mean, yeah. So we only have one local maximum. So local maximum is equal to global maximum. So that is the likelihood function of logistic regression. So this is the likelihood function. Likelihood of logistic function. So if we have parameter space may be multidimensional, but the parameter space, and we have the likelihood of beta. So this is actually the concave. So we only have the one local maximum. So the local max is equal to local max is equal to the global max. So we don't really have to worry about this kind of situation, such that if we use the derivative to find the optimal method, it does not really reach the local maximum. So here the local maximum is not equal to global maximum. So in this case, the estimation of beta is usually difficult, because usually optimization procedure is just finding the point which has the derivative equal to 0. So sometimes it reaches the local maximum by maximization, the optimization procedure. But this doesn't really happen for our logistic regression case. So only this case happens. So even though this is complicated, still it has some good properties. Yeah, so this is the estimation of the logistic regression. And maybe we have some examples here. So here is the typical situation of the X and Y in logistic regression. So X is numerical predictor. Here, right? And the Y is the response. And the Y is a 0 or 1. And this is the data for 100 observations. And you can see that the more observations around X is equal to 0 if Y is equal to 0. But the observations are slightly larger, maybe ranges from maybe 0 to maybe 2.5 for Y is equal to 1. So we have different tendency. So that means the X is large, Y is more likely to be 1. So I would say that the probability of Y is equal to 1 is higher. So we can fit the probability like this. So this is the probability of success. The probability of Y is equal to 1 if X is given. So we want to fit the logistic regression model. And the logistic regression model, we have to use the generalized linear model function, GLM function, not LM. And also, more importantly, you have to specify this option. Binary is equal to the logit. If you miss this binary logit, then actually the GLM is the same as LM. And then actually the format of regression is the same, just Y tilde X. That is the same as linear model, but you have to use the GLM function and the binomial logit. And you have several different options for link function, such as probit and the quotient and the complementary log. I think several options, but for now, I mean, in this class that we only use the logit function. And this is the result. So intercept and X. Okay, so basically this is logistic regression model. So the f of y, f of pi is equal to the alpha plus the beta 1.27 times x. So this is the model. And it is a little bit hard to interpret this because we have f here. So what this 1.27 means. So x increases by 1, f of pi increases by 1.27. F of pi is the transformed probability. So we are not really sure how much pi increases. But at least you can interpret this as larger x means larger f of pi. So that means larger pi, right? So the larger x implies larger f of pi, and f is monotone function. So this means the larger pi, monotone increasing function. F and f inverse are both monotone increasing function. So at least, okay, so this coefficient is positive, then larger x means larger y. And that is consistent with the previous graph. And you can also see this standard error of this estimate and the z value. In linear regression, this is called the t value. But the logistic regression, since the function, the likelihood function is very complicated, so the approximation by t-distribution does not apply. So we have to rely on the fact that if sample size is large enough, then this value, this distribution is approximated by a normal distribution, standard normal distribution. Then we have p-value. P-value is very small, so that means the x is a significant factor to explain y. So larger x certainly increase the success probability. We will explain other things later. But AIC is understandable that we have likelihood function. So we have AIC value. You can compare it for future prediction performance. And this is the number of iterations. So to find these coefficients basically are the implemented some approximation, the optimization procedure, the 4 times. Yeah, so this is what I explained. Yes. And yeah, and here is the code to demonstrate what's happening behind the optimization procedure. So at first, I defined the inverse logit function. So I logit of x is defined by exponential function of x divided by 1 plus exponential function of x. Then, given data set, the y and x are given. We calculate the linear combination of x. Okay, so we want to optimize parameter. So we want to develop a likelihood function of this parameter beta. So beta is equal to, beta is a vector consisting of beta naught and beta 1. And we want to optimize beta naught and beta 1. And what's the likelihood function? Actually, the negative log likelihood function. So this is negative log likelihood function. This is minus.ll. Negative log likelihood function of beta is defined by this. So this is, okay, so you can see that this is failure probability. So this is the failure probability 1 minus pi I, and this part is pi I. And for this data, the first 50 observations are failures, and the last 50 observations are success. I think that, right? So y is equal to 1 for last 50 observations. So yeah, so the likelihood function is the pi I for successful cases and 1 minus pi I for failure cases. So that we take logarithm and take summation and put negative sign, then we can get the negative log likelihood function. We want to maximize log likelihood function, so we want to minimize the negative log likelihood function. So we can use this optimum function to optimize this parameter. We have to give some initial estimates. So I just put arbitrary number, negative 0.2 and 0.5. And then we put the likelihood function here. Then we get the estimate for beta naught and estimate for beta 1 hat. And this is the value of likelihood function. Value of negative log likelihood function. And actually these estimated coefficients are exactly the same as the GLM output, you can see. So these numbers are the same as, so these numbers. Maybe some rounding errors, but we have this. Yeah, so this is how logistic regression, estimation in logistic regression works. And you can also define the confidence interval for the estimates. So since the function is more complicated, we need some computational functions to find the confidence interval. So this is actually based on the derivative and the second derivative of the likelihood function, but in terms of the R implementation, that you can use the confint.default function or contint function to get the confidence interval. So basically, the second method is more accurate than the first method. So, but the first method is probably faster. They're using some normal approximation, so this is more accurate. And this is faster. And this is one result. So this is the GLM object, so logistic regression model. Then you can put it in confint.default function. Then we can see that the intercept is between negative 1.17 and negative 0.10. So original estimate is negative 0.64. So beta naught is equal to 0.64, negative 0.64. So, but we can at least say that the beta naught is negative, significantly negative. And range for X is 0.71 to 1.83. And the beta 1 hat was 1.27. So, but we are sure that that number is between 0.7 to 1.83 with 95% confidence. So yes. And actually, these are just the estimated by coefficient plus minus the z value times standard error. So this is the z value for 95% threshold. So z sub 0.975. And this is estimate beta naught. So this method just uses normal approximation. So the normal quantile points and the standard error and the estimate itself that makes these numbers. And the more accurate one is conf.int. So this reflects some information which makes the interval asymmetric. So this interval is not centered at negative 0.64, and this interval is not centered at 1.27. So we can say that the 1.27 and this is 1.27 minus 0.51 or 52, and this is the estimate plus 0.62, so it's not symmetric. Yeah. So since this is more accurate, you can just use it unless the computational time is not too long. Any questions? I got one question. So does it have to be centered to be the most accurate? No, you don't really have to be, the interval does not have to be centered. So the second method is more accurate. Sometimes our confidence interval or prediction interval is not centered at our estimate, right? So for example, you are thinking about buying a car and a new car, and average price is about, I think, like the $48,000, right? $48,000. But what's the exact price for your car? And the maybe lowest possible case is around maybe $20,000, right? Maybe like the Mitsubishi Mirage or something. But the expensive cars are really expensive. You buy a Rolls Royce, then probably it will cost like the $400,000. And that range, 20,000 to 400,000, are not centered at the average value of the 48,000, right? So that can happen, and that situation is more realistic, and it reflects more information. So basically, the similar thing happens. So this is the estimate. So for the logistic regression, so it's not very similar example, but still the something is not centered at the best estimate. So that is possible. Yeah, good question. Okay, so if you don't really have other questions, that I go to some other materials. So in linear regression, we have the y is equal to beta naught plus beta 1x. Okay, so and then we estimated this. Then maybe we have the error term as well. We can use these two estimates, beta naught hat and beta 1 hat, to get estimate for y naught when we only observe x naught. So estimated y naught is equal to this number. And for logistic regression, we can do the same thing. So just that so this is, in short, the x beta hat. And x beta hat is also used in logistic regression. But if you want to transform this into estimated probability, we have to use F inverse. So this is estimated probability. Estimated probability of the probability of y is equal to 1 given x value. X may be a vector, the x value. So we have to use the F inverse. And the fitted value is obtained by fitted of GLM1. So this is the same as linear regression, just the object, and we put object within the fitted function. And more manually, you can extract the coefficients, and you can multiply x value. And we use the ilogit function, that is F inverse. Then we get the probability. So this number and this number are the same. So we calculated fitted probability for existing 100 observations. And the fitted curve over the scatter plot is here. So we have actual observations around here, but we have fitted probability. We can see that the larger x value means the more higher probability that y is equal to 1. So for example, if x is equal to 1, then success probability is about maybe 65%. So we can see that in this way. Yeah, we can overlay the graph by putting like this. So this is scatter plot. Of x and y. Then fitted curve is here. So fitted values. So this is fitted curve. To make fitted curve, you want to order the observations of x. So basically, this curve is made by 100 points, by connecting 100 points, that is fit the value for actual these 100 observations. So, but the you have to order it to make the graph make sense. So if we have multiple observations like the here and 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 the here, you want to connect in the order of X, right? So if you don't connect in the order of X, then the basically, you know, the graph looks like this. So we have slight overlap like this, right? So it does not look usual curve. So we want to connect in the order of X value, right? So we have to order those observations. And yeah, there are some tricks. So we have to specify the limit. So the range for Y as 0, 1, and range for X as minimum of X to maximum of X. And we have to specify it in both plots. Otherwise, the two, you know, the X scale and Y scale are not consistent. So that we have to make it in this way. Maybe simpler ways possible, but this is what I came up with. Yeah, I think that this is almost the everything about just fitting the logistic regression. And the 13.3 is another version of logistic regression. It's almost the same, but the data is input in a different format. And 13.4 is about testing. Do you have any questions about 13.1 and 2? No, we don't have any questions so far. Okay, so the next one, we consider the case that the predictor values are categorical. So here we have the predictor x1 and x2. And x1 is either no or yes, ny, ny, ny. And predictor x2 is also categorical, either A or B or C. So in this case, many observations may have the same pair of x1 and x2, maybe x1 no and x2 A. And suppose we have 50 observations with x1 is equal to n and x2 is equal to A. And the 3 of the observations are successful out of these 50. Then, you know, we don't really have to put the 50 lines to represent this data. So just we have to give the success, you know, the proportion of success here. So 3 out of 50 is just 0.06. So this data format is more concise. So we have the same thing for other pairs. In total, we only have the 6 possible pairs. So all observations are either of these 6 cases. And suppose that the number of observations for each case is 40, 30, 35, 15, 20, then we can just count the number of success here, and we can make proportion. Then this table should have enough information to do logistic regression of, you know, success probability on XY and X1 and X2. Yeah, and yeah, so just suppose that we have this data, then actually we can do logistic regression just by this way. So GLM, the same function, and the proportion. Proportion is the column of proportion that was 0.06 for the first case. Then we put the tilde x1 plus x2. Then we can fit the logistic regression. Binomial logic, that's the same. But we have to give the weight density because we have 50 observations. So that means we need the weight of 50 for this. So we have to specify this. But except for this, basically the format is the same as logistic regression discussed in 12.2. I got another question. Is logistic regression only for binary outcomes? Yes, so only for binary outcomes. So if we have more than 2 levels, it's much more complicated model. So we have so-called multinomial logistic regression. And the some other distribution like the ordered logistic regression, if the response has multiple levels but ordered, such as the rating from 1 to 5. So we have the different models, but we don't discuss that in this chapter. So maybe only thing you can do is the logistic regression in multiple layers. So suppose that we only have 3 levels, A, B, C. Suppose that A, B are closer, then you can do logistic regression for A, B versus C. Then second logistic regression for A versus B. So that is possible way, but we don't discuss other method. Yeah, you can search for multinomial logistic regression or ordered logistic regression for more complicated cases. Okay, that's a very good question. And yeah, here we can just see results here. So logistic regression works with this summarized table as well. And here, yeah, so here actually these x1 and x2 are categorical. So this intercept is the baseline for x1 is equal to n and x2 is equal to a. So again, without specifying the levels option, the R interprets this in alphabetical order. So n comes earlier than y and a comes earlier than b and c. So x1 is equal to n, x2 is equal to a is the intercept, and the baseline case. And this is the additional portion when x1 becomes y. And this is additional portion when x2 becomes b from a. And this is the additional portion that x2 becomes from a to c. So this. So in terms of the transformed probability, so b is 1.04 higher than the baseline a, and the c gives the 2.25, the higher transformed probability than x2 is equal to a. And you can see that these are significant. This one and this one are significant. So that means that a versus b is significant, and also a versus c is significant. But the x versus y is not significant. Sorry, n versus y is not significant. Yeah, so you can interpret it in this way. Yes, so now that we do the testing on logistic regression. So remember that in linear regression, we can compare the model such as y is equal to beta naught plus beta 1x plus epsilon against alternative hypothesis of y is equal to beta naught plus beta 1x1, maybe x1 here, and beta 2x2 plus epsilon. So you can test h against h1. So in this way, we can check the significance of x2 when we account for the value x1, right? So when I think that many years ago, like 40 years ago, the Japanese people say that if you have the good breakfast, I mean, at least if they eat breakfast, then their academic performance is better than the students who didn't eat breakfast. Okay. But that is affected by maybe the family situation, such as income level or something. So we want to see if really breakfast is important for academic performance. Y is academic performance. X2 is breakfast. And when we consider the income level of the family, whether breakfast matters for academic performance, then we can test H0 against H1. That is more comprehensive analysis than just checking the regression model y is equal to beta naught plus beta 2 x2. So in this case, maybe x1 is a confounding factor, and seemingly x2 is useful, but when x1 is introduced, possibly x2 becomes insignificant. So we can see the actual situation if you compare these two models. And we want to do the same thing for logistic regression here as well. So the H0 is here, the y is equal to mu plus beta j plus epsilon, and H1 is y is equal to mu plus alpha I plus beta j. So we want to see if really alpha I matters for y. Then we can do the so-called the deviance test. So we want to do the deviance test. So yeah, so the for linear regression we can do that, but the to make sure that for linear combination to compare this, that we can use the F test. But the F test is based on the fact that the observations are, the residuals are normal. The error terms are IID normal, independent and identically distributed normal. But in logistic regression, that we cannot really use that assumption. So because anyway, so it's transformed with probability or something. So we have to use the likelihood function to develop a test similar to F test. So that is the idea. And that we can use the deviance. And the deviance is a kind of transformed version of the likelihood function. Yeah, so the D quantifies the overall fit of the model. So to be exact, the D is given by this formula. So basically, this is similar to the fit of the model. So the D is equal to 0 is the perfect. It's similar to the situation that error is 0. And the D becomes larger when the fit is poor. And this quantity D, a kind of likelihood. So this quantity D actually follows the chi-square distribution with the degrees of freedom n minus p minus 1. Here, n is the sample size, and p is the number of predictors. Number of parameters, I would say. So number of parameters. So in continuous predictor, the p is just the number of predictors. But if the categorical predictor, sometimes we have the multiple levels, then we have multiple predictors for the one categorical variable. And this D can be calculated for each logistic regression model. And if we want to test the difference between two models, then we can calculate the D1 for model 1 and a D2 for model 2. And the theory suggests that the D1 minus D2 follows the chi-square distribution with DFQ. Here, the Q is the difference in the number of parameters between model 1 and model 2. So in this case, the model 2 have two more parameters because we have beta j, where j is equal to b and c. So actually we have the one baseline. So we have one parameter for alpha i's and one parameter or two parameters for beta j's. So in this case, the D1 minus D2 should follow chi-square distribution with DF2 if the beta j is the true beta j is equal to 0. So in this way, we can test these models. So if chi-square value is large enough, then basically the beta j is significant. So D1 minus D2 follows chi-square Q, but the larger difference between D1 and D2 indicates the significance of beta j. So if this value is large enough, then we reject null hypothesis of beta j is equal to 0 for all j's. So if D1 minus D2 is large enough, it implies additional parameters, beta j's, are significantly useful for beta fit. So this idea is summarized by analysis of deviance table. So if we put the GLM object in ANOVA function, it returns this deviance table. So this gives the deviance. So at first, this is the deviance. So deviance of, sorry about that. So this is the D1, this is D1, and this is D2. And this is the difference between D1 and D2. So D1 and D2. And the, so degrees of freedom is 2 here. So this D1 minus D2 follows the chi-square distribution with DF2. And 20.7 is pretty large value compared to degrees of freedom. So remember that expectation of chi-square distribution with DFK is equal to K actually. So D1 minus D2 is typically around 2, but actually in this case, actually 20.7, it's very large. So it's very significant and the p-value is much less than 0.05. And this table is similar to ANOVA table. So the test is sequential. So we test the difference between null model and X1 and the model with X1 and the model with X1 and X2. So we have 3 hypotheses, I would say H0 and H1 and H2. H0 is Y is not explained by anything. H1 is Y is explained by the X1. So maybe I would say the intercept, so just 1. Intercept plus X1 and Y, H2 is Y follows. Y is explained by intercept and X1 and X2. So the test is from here to here and here to here. So, and the p-values are this and this. So actually the X1 may not be useful. X1 has the p-value of 0.06. So X1 may not be useful. And if we change the order of the test, you can see the order of X1 and X2 are different. Then the test is different. So we compare null model Y on intercept and with Y on X2 only. And that we maybe H1 prime and H1, H2 prime. So X1 plus X2 here. So this test and this test are different from the previous table. And in this case, the X2 is certainly useful, but actually the X1 doesn't have much additional information to X2 with p-value 0.13. So these 2 results are different because the test is sequential. The order of variables matter. So in practice, you want to put some variable which should definitely affect Y first. Then after that, you can check whether X2 has additional information on X1. Yeah. I got one question. What does the INC dot mean under B11? INC1, where's that? INC1. Maybe. The previous slide, which slide? 25, maybe 24. INC. 23, slide 23. Oh, INC. This is just the specific case, the income. So suppose that the academic performance is explained by income. This is actually the common variable. And this is the whether or not the student eat breakfast. So yeah, so in this way that we can check whether the breakfast has additional power to explain academic performance, given information of income. Okay, so yeah, and the previous figure can be calculated. The p-value can be calculated by the probability for chi-square distribution function. So chi-square distribution with df2. So chi-square value, we have this kind of distribution, and we have 20.7. This is the PDF of chi-square. And we got the p-value of the very small, the 3 times 10 to the power negative 5, but this probability is calculated by this. So we can use 1 minus p chi-square function. And yeah, and this is the last slide. So yeah, so the test is sequential. So if we change the x1 and x2, the result may change. So the implication is x2 is highly significant in any case. And x1 is marginally significant only if x1 is introduced first. So if x2 is not in the model, x1 is significant. But if x2 is already in the model, x1 is not significant. So that is the interpretation of results. Okay, so that's chapter 12. So I think that's it for today. I think just make sure that I covered enough materials for quizzes. Regression report. Yeah, how many observations? Yeah. Sorry, one thing I want to mention is that how to use the logistic regression results. So we get the fitted probability, such as 0.4, 0.6, and 0.3, 0.1, 0.1. And usually, to predict y, we set the threshold at 0.5. So 0.6 and 0.9. 0.9. So we estimate these will be successful. And the 0.4, 0.3, 0.2, these will be failure. But really, it depends on the situation. If you want to estimate the probability that the one student die within 1 year or something, if that's that kind of serious rare event, maybe you want to set threshold at 10% to make warning if some students have more than 10% probability to death by some health reasons or something. Yeah, so the threshold used is usually 0.5, but sometimes you can get the different threshold. And once you get threshold, you can calculate the actual y, 0, 1, and the predicted y. Then you can make a table such as like this, the table of counts. Then you can see this prediction is good because we have 130 cases that we predicted correctly, and we missed 15 cases. So once you specify the threshold, that you can make the table of the predicted results. Okay, so that's it for today. And if you don't have any questions, see you on Thursday.